Okay. Um, all right. So the final is going to be the Thursday of finals week. Nice way to end your semester-long suffering. Probably should confirm that beyond a shadow of a doubt. And it is comprehensive, kind of. Because basically the course breaks down into three major parts. We have chapter 13, that was all about partial derivatives. Chapter 14 is all about multiple integrals. And chapter 15, that we're in now, vector calculus. Most material will be on chapter 15. There'll be 15 problems altogether. Most will be on that. There'll be some problems on multiple integrals, and then one problem on Lagrange multipliers. And the practice final and its solution are on the lectures page, very bottom. So I'll just put up a little while ago, so you can see what's in store for you. So the way I'm going to work this, because I like to make all the problems worth the same number of points. So there are 15, which doesn't really work well with 100. So I'm going to make each problem worth 7 points, so for a total of 105. But I'm going to still make a final out of 100. So if you got everything right, you'd actually get a 105%. So I throw a little freebie in there. Okay, and of course, since that's the last day of finals week, I give you some. All right, so now we can move forward with the next section. Okay, so this is kernel and divergence. Now, in Cal 3, you learn about certain vector operations. There's dot product and cross product. And so I'm going to show you new operations on vector fields, kernel and divergence, that make use of dot product and cross product. So in other words, if you don't understand or remember dot product and cross product, you're dead in the water. So I'll refresh your memory now. We're going to be using these a lot. With dot product, u dot v would be multiply corresponding components and add them all up. And the result is a scalar or number. Okay. The cross product, and so I'm assuming here that u has components u1, u2, u3. V has components v1, v2, v3. And I probably should have chosen different letters than u and v, but I'll do my best to make sure my u's look nothing like my v's. I'm not sure. Yeah. So dot product, u cross v. Actually, I've written it down here. That is a vector. And for three-dimensional vectors, if you have two-dimensional vectors, what you would do is you would add on the z component of 0 and then do the cross product from there. So what we get is u2v3 minus v2u3. Then we have u3 v1 minus u1 v3. And finally, u1 v2 minus u1 u2. Actually, you can rearrange it so it's more consistent. Okay. All right. Now, I should mention, when you look at the practice final, I have put in a formula sheet. And because it's for a whole semester, it's somewhat extensive. And like for instance, this cross product formula is going to be on it. The major theorems are going to be on it, like Green's theorem and other ones that we'll see later. So there won't be as much to memorize, but still it's important to understand how to use all these things. So at least you'll see what you don't have to commit to memory. Okay, now I'm going to define a vector field in 3 dimensions, F. As usual, I have components P, Q, and R. They're all functions of X, Y, and Z. And then I'm going to define a very strange vector, and it's referred to as del. It's an upside down delta, like a gradient symbol. And its components are not functions. They're actually partial differentiation operators. So we have partial with respect to x, partial with respect to y, and partial with respect to z. So what's going to happen is I'm going to carry out dot products or cross products involving these 2 vectors. And here we're multiplying components. It's just ordinary multiplication of numbers. Here, if I'm multiplying a function by a differentiation operator, I'm carrying out that differentiation. Now, you'll see this when I actually define these, these new operations. Okay, so the first operation of interest, the simpler one, is the divergence. Of a vector field F, which is abbreviated as div F, is defined in terms of vector operations as the dot product of this del vector with F. So if I write this out component by component, I have ddx, ddy, ddz, dot p, q, r. So now I multiply corresponding components and add them up. So I have partial with respect to x of p, so that's like a product of these 2, plus partial with respect to y of q, plus partial with respect to z of r. So that's it. That's the divergence. So notice the p, q, and r are the x, y, and z components of its vector field, and they're differentiated with respect to the corresponding variables, px, qy, rz. So there's a obvious pattern there. Keep in mind. The divergence. So at any given point x, y, z. The divergence is going to be a number. What does that number mean? So the interpretation if the vector field F is the velocity field of some fluid, so PQR indicates at any particular point the vector, the direction in which the fluid is traveling at that point, then you have different interpretations depending on whether this divergence at a particular point is positive, negative, or 0. So if it's positive, then the fluid is moving away from this point, x naught, y naught, z naught. And that's why they call it divergent. It's diverging away from it. If it's negative, then the fluid moves toward x naught, y naught, z naught. Then if it's equal to 0, then you really don't have either one happening. In fact, this condition of the divergence of a velocity field being equal to 0 is used to classify a fluid as incompressible. Okay. So that's one operation we'll need. Now, the other operation, instead of using a dot product, uses a cross product. So the curl of the vector field F, which is this abbreviated curl F, that is the cross product of this del vector with F. So if I write this, I usually like to write cross products to help me keep everything straight. I like to write one vector on top of the other. Okay. Or you can use a formula over there. You just have to keep in mind, like before, products of differentiation operators and functions are just partial derivatives of those functions. So what I would get is, so this times this, so Ry minus Qz is the first component. And then for the second component, I had this times this, so Pz minus ddx times r, so minus rx. And then these two, qx minus py. Okay. All right. Now, this time the result is not a number, it's a vector. So what does this vector mean? So the interpretation there's two things to look at because it's a vector quantity. There's a magnitude and a direction. So the magnitude of curl F indicates the tendency. Again, this is for a case where F refers to a velocity field of a fluid. So it's a tendency of a fluid to rotate around any axis. So is there any vorticity? Is there any swirling going on? The direction of curl F, that's the axis that it would be rotating around. So if curl F turns out to be quite large, then there's a lot of vorticity at that point, and you can tell from a direction what is the axis that it's swirling around. Now, one case of interest, okay, I talked about what happens if the divergence is 0. What about the curl? The curl of F is the 0 vector. That means that there's no axis of rotation whatsoever. So we say that F is irrotational. Now, I've used this term before. So if the vector field is irrotational, what is the other term for it that we've actually used more often? It's conservative. Now, earlier, a couple sections ago, I told you how you can check if a given vector field is conservative. And you had to match certain partial derivatives. Like for a two-dimensional vector field to be conservative, you needed qx equal to py. And then for 3 dimensions, it turned out you actually needed this to equal this, and this to equal to this. So the test I gave you for checking whether a given vector field is conservative is equivalent to simply saying, well, the curl of f has to be 0. So if the curl is 0, it's conservative, and then you're able to find a potential function. So I just didn't give you the term for it until now. So now you've learned like really the 3 essential vector calculus operations on functions or vector fields. I mean, we've been using gradient for quite some time, and we'll see more of that. But so there's gradient, there's divergence, and now there's curl. In fact, there actually is a very well-known textbook on vector calculus, and the title is literally this: div, grad, curl, and all that. So. Okay. Now, there are certain simple relationships between these 3 operations, divergence, gradient, and curl, that are good to be aware of. Okay. So, div, grad, curl. Okay. Now, suppose, okay, so if f is conservative, now we know 2 things. First of all, its curl is 0, and f is the gradient of some function little f, that are referred to as a potential function. So if I go ahead and substitute that in here, I get the following. It's the curl of the gradient of any function is the 0 vector. So that's something that's just true in general. Any scalar valued function, take its gradient and you get a vector field. Take a curl of that, you'll get 0. So this is often how it's given in words in any textbook. Okay, so the curl of any gradient is 0. All right. I guess if this were like an elementary school class, I'd make you all repeat that. Now, another relationship is that because if you take a vector field f, you take its curl, you get another vector field. And then you can take the divergence of that, because the divergence is applied to a vector field. And what you can show is the divergence of any vector field that is a curl of another one is always 0. Okay, so the divergence of any curl is 0. All right, so 2 things to keep in mind. Okay. And I didn't bother proving every one of these in the notes. First of all, you can piece together from things that are already in there. But this is something that you can verify directly just by taking the appropriate partial derivatives. So what happens is, what is curl of f? You can see over there, it's various first partial derivatives of the various components, p, q, and r. And then you take the divergence, and then you're going, what happens is, you're taking derivatives of those, so you get a bunch of mixed second partial derivatives. And mixed second partial derivatives involving the same variables are equal, and that's how you can show that everything cancels, you get 0. Now, here we have 3 operations. You might think, okay, well, there's 6 ways to combine them. Are they all 0? No, they're not. In fact, some combinations would not make sense. For example, it does not make, while it makes sense to take the divergence of a curl, it does not make sense to take the curl of a divergence, because a divergence is a function and curl requires a vector field. But there is one more combination, while it's not 0, it's of interest. The divergence of a gradient of some function Well, that would be the divergence of the vector field fx, fy, fz. And what is a divergence? A divergence is the dot product of ddx, ddy, ddz. So dot product of that with the gradient fx, fy, fz. So if we go ahead and carry out this dot product, so what you do is you multiply, really you apply these differentiation operators to these functions and add them all up. What are you going to get? So if I apply this differentiation operator to this partial derivative, what does that give me?
X, Y, and Z.
What?
X, Y, and Z.
No.
The sum of the second partials.
Yeah. So this would be ddx of df dx plus, I'm not sure if this is what you were saying earlier, but df dy plus ddz df dz. So you get all second partials where it's with respect to the same variable twice. So there are no mixed partials here. So what you get is fxx plus fyy plus fzz. Now, this is actually very important. This is the Laplacian of f. And it's abbreviated in various ways. Sometimes it's delta f, also the gradient symbol squared times f, and that comes from the fact that it's literally del dot gradient of f. So it's written in all of those different ways in different textbooks. So Laplacian f is very important because it comes up in various partial differential equations. Now, I know not all of you have taken differential equations yet. Some of you are suffering through it now. I've heard. So, there that's ordinary differential equations. You're only taking derivatives with respect to one variable. When you have functions of several variables, you have differential equations that use partial derivatives with respect to the various variables. So, for instance, Math 417 covers that. And in all of the essential partial differential equations, Laplacian plays a role. So in fact, at the very end of the semester, I'll be deriving one of those equations called the heat equation. And actually, other combinations of these operators either don't make sense or are not really anything of interest. But these are the main three. Okay. Right. Now, okay, so now that I've defined all of those. Okay. So now I'm going to revisit Stokes Theorem. So using these operations, curl of divergence, there are now different ways to express Stokes Theorem that are equivalent to the original. And that's going to help us when because Stokes Theorem is a two-dimensional theorem. But we need to generalize it to 3 dimensions, and there's actually going to be 2 ways to do that. Just like how with polar coordinates, this is for 2D, and we generalize it to 3D in 2 different ways to get, whoops, sorry to whoever's watching a video, to get cylindrical and spherical coordinates. Now, suppose we have a vector field that's really a 2-dimensional vector field, but we make it 3 dimensions by adding on a z component that is 0. So, if I were to take the curl of this vector field. So this is my R. That's 0. Also, keep in mind that P and Q are functions x and y only. So they do not depend on z in any way. Because all we're doing is we're starting with a two-dimensional case, and then I'm just throwing in a 0 component so that the cross product will make sense. Now, so if I recall the formula that I put down earlier and have since erased, as I feed off people's lost attendance points. Okay, actually I feed on Chick-fil-A, but that's for after class. Now, so the component, so the curl is, okay, so ry minus qz, pz minus rx, qx minus py, but that's 0 because r is 0. That's 0 for the same reason. These are 0 because p and q depend only on x and y. So pz and qz are both equal to 0. So the first two components disappear entirely. So the only thing that's left is 0, 0, qx minus py. Now, another way of expressing that is I can write this as qx minus py times the vector 0, 0, 1. Although in physics land, what is that? This vector, what do we call that? Nobody?
Wait, what?
This vector, 0, 0, 1, z-axis.
I'll just a vector.
Yeah, what's the name we call that? Like, especially in physics.
Oh,
K, yeah. So it's qx minus py k. All right. Now, okay. So then, if I have the line integral of a vector field f over a curve, and yes, I messed up last time. This is the circulation, not the other kind. Around C. Then by Green's theorem, and we assume that C is oriented counterclockwise, then by Green's theorem we get, and C is some closed curve that's enclosing the region D, and what do we get? That's qx minus py. That's just what Green's theorem gives. But another way of looking at that is the double integral over D of the curl of f dup, which is the same as qx minus py times the vector k, dot product with k, where, now if I do a 3D view, here's my region, it's sitting in the xy plane, D, and then I have this vector, whoops, that, oh God, almost Friday for me too. That's pointing straight up. This is the normal vector to the region D. But since D is flat, it's sitting in the xy plane, what is this vector? Like what's based on the direction it's pointing in? Yeah, z-axis, so that's a vector called k. This is k. If we make it like the unit normal vector, so magnitude 1. So what we have here is, if I use n to refer to the normal vector, it is the double integral over d of the curl of f dot product with the vector that is normal to the region. Okay, so in an upcoming section after we deal with surfaces in three dimensions, this will lead to a three-dimensional version of Green's theorem called Stokes Theorem. So when you specialize it to 2 dimensions, your normal vector is just k, and your curl is nothing but the last component, qx minus py. So this is another way of looking at Green's theorem that will lead us to Stokes theorem towards the end. So curl gives us another way of describing it. Because Green's theorem allows us to compute the circulation in another way that might be easier. But that's for a flat region. What if you have a three-dimensional surface? Think like a Lay's potato chip. Okay. I said Lay's because one, I like it better, and two, because it's very irregular. And that chip has a boundary. So you think of that as a region with a closed curve as a boundary, and you want to compute the circulation around that. You need a three-dimensional version of Green's theorem, and that's what this gives. Okay. But there's another way to generalize Green's theorem using the divergence. Okay. All right, so as soon as I finish this page, we're all done. And I hope I'll see at least some of you on Monday. Okay. And that's the unfortunate asymmetry, because if even one of you is here, then I have to be here.
Are you encouraging something?
It doesn't help me
We can make a deal.
because
Sorry, you guys.
I'm not traveling until Thanksgiving Day, and I have stuff I can't get out of on Tuesday anyway. So.
Well, I'll be here, so.
Yeah.
Sorry.
Okay.
We have class on Monday for
Okay.
Chin.
So now, same situation. F is a two-dimensional vector field, P and Q. Therefore, the divergence of F would be this with respect to x plus this with respect to y. So I go ahead and fill that in here. So if I'm integrating this over the region B, okay, then and what I'm going to do is I'm going to write the original form of Green's theorem down here. So we have qx minus py is equal to the line integral p dx plus q dy. But here, p and q have different meanings. So p down here is equal to q down here. Q up here is equal to minus p down here. So, so if I keep in mind the difference, then I'm not going to have p dx plus q dy up here. I have to make changes. So what I'm going to get is, okay, okay. So what I'm going to get is p dy minus q dx. And to see that, if I change q to minus p, I have that. If I change p to q, I have that. So these two are saying the same thing, just using different notation. So this is still Green's theorem. It's expressed differently. And the important thing here is I wanted the plus here instead of a minus, because that's what I get from divergence. Okay, so this is a different sort of line integral. This is not the circulation of f around C. So if I write this in parametric form, then what I get is P of my parametric equations, and then I have y prime of t minus q of r of t, x prime of t, dt. And then what I'm going to do is I'm going to divide and multiply by the magnitude of my tangent vector. Okay. So now I can express my integrand as a dot product of these two vectors. So I'm going to have P and Q. Dot product with this vector, y prime over the magnitude of my tangent vector, and then minus x prime over magnitude of my tangent vector, magnitude of my tangent vector. Okay. Now, this is my vector field F again. But what is this vector? Because x prime, so if I have my region here in the plane, at any particular point, okay, I want counterclockwise orientation. So this vector is x prime, y prime. That is t, the tangent vector. Now, actually I should not write it over here. Alright, so that's a tangent vector. Now, how do I get a vector that's perpendicular or orthogonal to this one? All I have to do is swap the components and negate one of them. So I could, for instance, take this one or this one. So this vector right here, okay, so I have y prime, x prime. So in this case, it is, okay, yep, that's the right orientation. Yeah. So what I have here is, this one is negated, because the y coordinate's going down, so it's instead of up. So that's y prime minus x prime. Or I can flip it around. I have minus y prime, x prime. So both these vectors are perpendicular to this one. I'm going to choose this one. This is the outward normal vector. Outward because it's pointing outside the region. Here, I can write this as the integral over a curve C of f, dot product with this. This is that same normal vector, except for one thing. It's normalized. So that would be n. So this right here, I'm labeling as n. This is the outward unit normal vector. And then this right here is ds. From our first brush with line integrals of scalar valued functions, you had that expression square root of x prime plus squared plus y prime squared plus z prime squared times dt. That's ds, the element of length along the curve C. So now we have another version of Green's theorem. And if F is a velocity field, this is the flux F through the boundary of the region D. So you have fluid that's crossing into the region, has to cross through the curve C. So the flux is a measure of how much fluid is passing into the sorry, not in, outward, because it's outward unit normal. So it's a fluid that's crossing through the boundary to go out. So the outward flux. is what this line integral gives. So that's the difference between this line integral and this line integral. This line integral gives circulation around the curve C. This gives flux through the curve C, through the boundary. So that's why I mentioned in that document I posted the other day, which hopefully you've looked at. Now, this is the circulation form, and this is the flux form of Green's theorem. Okay. So, to summarize, all right. What we have is the other 3D version of Green's theorem is that the integral over the interior of a divergence of a vector field is equal to the integral over the boundary, bless you, of the normal component of that vector field. So the flux through the boundary is equal to the integral of the divergence in the interior. Okay. So words, that's what's happening here. So this will be generalized later to 3D, where now your interior is a three-dimensional solid, and your boundary is some closed surface. So like, think of a sphere. You have a fluid passing through the sphere, and you're integrating over the interior of the sphere, like maybe using spherical coordinates. And this leads to what's called the divergence theorem. So Green's theorem generalized to 3D gives rise to Stokes theorem in one case, and then divergence theorem in every case, and that's how we're going to wrap up the semester. But now we see how these operations, div and curl, can be used to come up with those generalizations. Okay, so starting on Monday, we start getting into 3D and learning how to, because we've been integrating over curves, now we need to see how to integrate over surfaces. And trust me, it's going to be a pain. Okay.